do another one. Sorry if I don't sound as lively today. It is a lot earlier than I usually wake up at due to the fact that I've got something else to do for the majority of the day. So I decided to knock at least two problems out this morning. Anyways, 207 course schedule. There are a total of num courses you have to take labeled from OK. You're given an array prerequisites indicates that you must take course if you want to take course OK. For example, OK. So in order to take this, you have to take this. Oh no, you have to take this before this. Okay. And return true if you can finish all courses, otherwise return false. Okay. So, in theory, it sounds like a decent candidate for topological sort. And I think this is a pretty common pet problem for a topological sort. But let's think about how to actually implement that then. Let's see. So there must be at least two courses to take. No, there can be one course. How does that work if there's one course? What does that actually return? I'm interested. Then it must be 0, 0, right? Okay. So, corner case, if one course turn false, course cannot be a prereq for itself. Though this corner case or this reasoning could probably apply to other courses as well. So, let's see. How do we do a topological sort? We find, in theory, we find the first, or find really any element that does not have any incoming edges. Then pull that element out, or yeah, and add its neighbors to be, or really just find the element that does not have any incoming edges and then pull that element out. And then repeat until you cannot find any more elements without incoming edges, which indicates a cycle, or until the list or the container is empty. How would we do it in this case? We could do something like find, let's see. So iterate over the prereq array, checking the second element in the pair, because that's the course that needs the prereq. Store, all the items within a set. We could probably do an array. And then if an item does not appear within the array, we can start by taking that course and then removing or adding that course to another data structure to indicate completion. So the idea is that we go through and we check to see, so we know that in order to take 1, or in order to take 0, we have to take 1. So we toss in 0. Then we check through the array, and we notice that 1 doesn't have anything inside of it. And this could probably be a... I'm tempted to say that this could be an array of booleans, but I'm not too sure. Because this one would be like, we would have to iterate into the prereq array every time to check. So that'd be O of n, because we'd have to scan through the array each time, times O of n. Or, yes, because there are potentially, or I'll say O of p, because I'm not sure if the number of prerequisites is bounded by anything that is even close to the courses, right? Though I suppose if there is only an n number of courses, then there must be at most, oh gosh, just trying to think. Yeah. There's probably some properties of graphs that I'm forgetting now, where there is a bound to the number of edges based on the number of nodes that exist within a graph. I can't remember that for now. So I'll say P. O of NP, and not the incomplete type time, which is actually pretty slow. But maybe we could cut down on some time by sorting, potentially, by the second element in the array. We could also cut down on some time by storing the prereq in a different manner, potentially. I'm going to code out the naive solution and then think about this some more afterwards. Is it possible for this to be like that? Oh. Because prerequisites could be size 0. Actually, if the prerequisite size is 0, then it really doesn't matter what size or how many number of courses we can take, because there is no overlap. So now we have to consider the other cases. So this is our courses taken array that will indicate the courses we have taken. And then we can say prerequisites for each course. We'll create a set has prereq. If course 1, or we can say has prereq dot at course 1, is equal to true, so we just set that course to have a prereq. Then we can say has prereq prereq. Course if course or so course prereq will be our array. If has prereq is true, or false rather. Next course to take, this starts at -1. Actually, we can just say courses taken at the index is equal to true. Right. So for all the courses that don't have a prereq, it's not true. So also this should be for each index as well. Actually, no, that makes sense. Because the course 1 is what we actually want for the prereq. The course is taken. So if our course is taken is not true, or is, yeah, so we haven't taken the left side course, then we set the right side course to have a prereq. Then we go through. If something doesn't have a prereq and we haven't taken it yet, then we take it. I'm starting to think whether or not just creating a graph itself of this would be an easier time. Because then you can remove things from that list. Has all courses been taken? Else if has prereq is true. But this doesn't do cycle detection. I know. Rather than having this rec list, this will be a list containing all classes that this it's a list containing all classes that the course is a prereq for. So we will say this is going to be a list of list int, where we create a mutable list of int. So this creates a prereq list for there, and then we can say prerequisites for each prereq pair. List at prereq pair at 0. Add. So we go to the list, the index that belongs to the prereq itself, and we say that this course is a prereq for, of course, the prereq pair 1. So now this prereq list is a list containing, so the index is the course number itself, and then the value is a list of all the courses that this prereq has. I wonder if I should flip it around. Still feels like a queue would be kind of interesting. Let's see. Right, I think I want to flip this around actually. So that for each course, we inside the list, and this will be a mutable list. Inside that list, we will say that it is a list of integers that will hold all the prerequisites for a course. Then we can say prereq list for each course. If the course is empty, this list of is of size num courses. List of lets us do that, right? Doesn't look like it. Yeah, we can make this an array, right? And if the course is empty, then cube of course is equal to or dot add course. This will be indexed. We want to add the index, which is the course itself. The index is list of parameters. And then we can say while queue of courses is not empty. So this queue of courses is not empty is going to indicate sort of the courses that we take. And we're going to have to repeat this again. So we'll say first of all, we'll do val next course queue of courses dot first, and then queue of courses remove at 0. Then for each indexed, of course if index is not the next course that we're taking, because there's no point in doing any calculations for that. Is there a contains prereq list contains course, or rather course contains the course that we're taking right now. Maybe there's like a find. I want a find that returns the index. It doesn't look like that exists. Okay. Then in that case, course for each prereq index. I'll put idx because I don't know if this will get shadowed. If prereq is equal to our next course, course dot remove at idx. So that just removes the next course. Then after all of that, we say if course is empty. Queue of courses add index. So basically we removed the prerequisites from here, and then we add it if it's empty. But what is our terminating condition? We can do a var has all courses been taken. It's false. And this is judged by the fact that I'm just thinking about this case now. No, because if queue of courses, it would have never added 0 because 0 has a prereq. Okay. We can do a prereq list for each course for the last time. We can say if course is not empty, or yeah. Set this to true. We assume that all courses have been taken. Then we iterate if any of the courses are not empty. Then we set it to false. And then we return has all courses been taken. Okay. So this is probably a polynomial time solution. I'm not sure if topological sort can be better than that, but maybe. So we have a few corner cases. We create a prerequisite list, which will be index will be the course index, the course itself, and then the value is the list of courses that we need to take before it. We have a queue of courses which we will use to indicate the courses that we have taken so far. The prerequisites will go through and we'll populate the prerequisite list. And then we'll check the prerequisite list to see if any of the courses are empty or basically have no prerequisites then. If any of them are, then we add them to our queue of courses. For each value in our queue of courses, we will take that and then we will say for each, I wonder if take actually takes the, it doesn't mutate it. Maybe drop? No, take is like the opposite of drop. Okay, never mind that. Then we check for each within the prerequisite list if we remove the prerequisite, basically indicating that we've taken the course. This is equivalent to removing the edge. And now if that course has no incoming edges, if it's empty, then we add it to our queue. Otherwise, we just leave it there, right? Because there are other prerequisites that we have yet to take. And we're fine with using this queue because after we finish a course, after we finish taking the course and removing the prerequisites from anywhere that it applies, then we don't really care much about it anymore as far as I think. Right? So we can just put it in the queue, process that node, or process that course, and then forget about it, basically. Then we check one last time to make sure that all the courses have been taken, essentially by checking the prerequisite list to see if there are any other elements which still have prerequisites that have not yet been taken. And if that is true, then we will return false, essentially, by changing this flag and then never changing it back. So I think this should work, but let's see what LeetCode thinks. So looks like, right, Java, or yeah, they're not a fan of concurrent modification. So within a for loop, you shouldn't modify this item. Hmm. Mm-hmm. I wonder if it's this entire block or if it's just this part. Let me see if it's just that part. If it compiles, then it's just that part. Okay, then it is just this part. Then we can say I'm not sure if we can actually get around this because we do need to modify the course itself. So this index is an int. This course is the list itself. I can try doing a standard for loop. If course at I is equal to next course, course root at I. This might still yell at me for doing a concurrent modification. Oh, it looks like we're gonna do a TLE. Interesting. Let's see. This course is a list of courses. Do I need to manually increment I? Yeah, print course here. Just to see what it's doing. Oh, I think it's because this queue of courses is adding, we should only do this if it's a new course, which means that it should be in here. Because if it's a course that we've already taken, if it's a course that we've already taken, therefore it's not new by removal, then we shouldn't worry about it. Otherwise, we'll run into that that concurrent modification exception, or not that concurrent, that infinite loop, because we'll just keep adding the empty item or empty items from before, right? So this seems all fine and good. Again, this runs in some flavor of polynomial, which I'm not sure if actually if that's the fastest that's possible. Well, in the case of topological sort, for sure we need to probably check, at least in the first place, we need to check all the nodes, right? To see which one has no incoming edges. From there, let's see. From there, we don't have to check all the nodes, do we? Just the nodes that we are attached to. Just the nodes that we have a connection to. So So the key here is the course value list of prereq. And I'm actually going to sacrifice a little bit more space for time by creating basically an adjacency list. So the key is the course, and the value is list of connected course, or list of courses that require this course. And our adjacency list prereq pair 1. So rather than searching through all of them, we can say adjacency list at next course for each course, prereq list at our course for I in 0 to course dot size minus 1 because it's inclusive. So for each course, we're going to say val prerequisites is equal to prereq list at our course if prerequisites at I is equal to our next course, then we want prerequisites remove at I. So this is basically the same thing, and if prerequisites dot size is 0 or is empty, then queue of courses add course. So course is the course that we fulfill a requirement for. Prereq is the list of that course's requirements. Remove that requirement. We've taken the course. And then we add it if it's empty now. So of the next course if we can now. So I think this makes sense. We've sacrificed quite a bit of space for that. There's probably a better way to do this. We'll see. I have a feeling that probably only one of these is necessary. But first, let's see if it actually compiles. Okay, looks like it does. Okay, but yeah, so we've used two adjacency lists, essentially the opposite of each other, one that has the outgoing edges and one that has the ingoing edges. So this adjacency list has the outgoing edges, and the prereq list has the incoming edges. And then we first populate these. We populate both of the lists, and then we check to see if there are any courses that within the incoming edges that don't have any incoming edges. Then we add that to our queue of courses. Then, for each course that we can take, we will check to see we can take that course, remove it from the incoming edges of all the nodes that have that it has outgoing edges to. And if that was the last incoming edge to that list or to that element, that course, then we can add it and take that course next. And then at the end, we just do one last check to see if there are any other nodes that have incoming edges that we have for courses that we have not taken. And if there are, then we just return false. If all the courses have been taken, indicated by the fact that all our courses have no more incoming edges, then we can say true. So let's give this a submit and let's see where we're at. I'm guessing that this is way too much space to use. And there's probably a way to cut it down, but we'll see. Maybe there's also a corner case that we missed. Index 1, size 1. Let's see. Interesting. So he broke at this line. Guessing prerequisites I. But this is going from between 0 and the size minus 1 inclusive. But if we remove a course, does this actually... We might need to do something a little bit unorthodox in order to recalculate the prerequisite size. because I'm not sure if this prerequisite size actually gets recalculated. I think that might be actually the issue here. Let's quickly run our code to make sure that we haven't broken anything major yet before tossing this in. This should be an index. This should be an index. Okay, so we haven't broken anything there. Let's see if this fixed the problem of our indexes being screwed up. Okay, cool. Looks like it did. Yeah, so I guess for loops don't actually recalculate the end condition after they've finished. After they've finished calculating, or after they've initialized that for loop, they don't recalculate like the end condition. Okay, so actually our runtime is fine, and our memory usage is actually also fine, which I'm happy about in that case. And I think I'm gonna leave it there for now. There are probably a lot more optimizations I could perform to this, but I just don't have that time today, unfortunately. So with that, I'm just going to leave this here. So we did outgoing edges, incoming edges, or yeah, first incoming edges, then outgoing edges, populate them, check to see if there are any courses that we can actually take without any prerequisites. For those, we remove the prerequisite and we check to see if there are any other courses that we can take now. If we can, we add them. And at the end, we check to see if there are any courses that still have incoming edges, and that indicates that we have not taken all of the courses. So, I hope you've learned something, and I will see you for the next problem.